Boom. Hello and welcome back to Calculus 1, finally, right? After 2 weeks, almost 2 weeks. So the topic for today, 3.6, derivatives as rate of change. So I said at one point, or multiple point probably, so far that calculus consists of limits, derivatives, and integrals, and derivatives measure change. We can detect using the slope of the tangent line, we can detect the change at a point. So we constantly change. For instance, those of you that are not familiar with the fact, you are the tallest and lightest during the day when you wake up. So your body worked out all of the food practically that you put in your system, right? And your joints all stretched because you were unconscious for a number of hours. So they stretched. So you are the lightest and tallest for the day when you wake up in the morning. As you go about your day, you will introduce food, which will make you heavier, and then also your upper body weight will compress the joints slightly. These are all very small changes, but they change the system, and over the course of the day, right, you get heavier and you get shorter, and then you go to bed again. So now you can think of other ideas, other concepts where the change happens. As you drive, for instance, the entire system becomes lighter as you drive from point A to point B. Why? You are converting your fuel, which was weight, into energy. So you explode all of those dead plants and animals in your engine, and then about 27% of that goes to move your car, because that's how pathetic our technology is. About 27% efficiency. So 27% of the gas that you burn is the one that energy that moves you from point A to point B, and the rest is all wasted on noise, explosion, friction, heat, and everything else that you don't actually use at all as you drive a car. So the change is there because you are constantly using fuel, and with this process, right, it's the chemical process of burning the fuel that you are converting the fuel into energy. So you have the change in the system. So there are many examples that you can use. Now we're going to take a look at rates of change in their default setting, should I say, the way that Isaac Newton developed these things, which is for physics and primarily to deal with path and with velocity, acceleration, and so on. And then we are going to take a look at other applications as well, growth models, population maybe, and then also take a look at some of the business applications that some of you might be interested in understanding the business. So the first the first part is to talk about the velocity and acceleration and those kind of things. So let's start with the, oh great, nice. Usually I can only do one experiment, I can do 6. So when you throw an object, the object will undergo the parabolic motion in time. So as I throw this marker, you are supposed to see a downward opening parabola as the marker goes through space, right? And it doesn't matter how hard I toss, right? If, as you can see, they're all parabolas. It doesn't matter how hard, because each single one of these had this path. Now, The difference was that some of these paths went like this. Some of the paths went really far. The last one went like this. That's still a parabola, even though it doesn't look like a parabola that you are used to seeing in your math class. It is still downward opening parabola. Now, there is a point at which the marker leaves my hand, and there is a point at which marker strikes the ground. So the initial, you have initial point, and you have terminal point. Now, if you are to put this in the coordinate system where your x-axis is going to be time, we are going to have a function for the height of the object described through, well, sorry, for the position of the object described through its progression in time as the independent input variable. So if I am to place this, so again, this is t-axis and this is the height y. Let's say that this is the 6 feet, which is, you know, where I throw things from, right? This is the 6 feet. Well, I mean, this is the 6 feet, but this is now 6 feet scale. You toss something and then eventually hits the ground. So now we should be able to get the function. It is a parabola which opens downward. Now, we do not have the tools to develop this function in class yet, so you have to trust whatever I give you. But soon enough, you guys will be able to, in Calc 2 already, but then differential equations definitely, to get this function from starting from one point. So right now, I will tell you that the position function s, right, is -1/2 gt squared plus v0t plus s, well, let's put y0, which is the initial height. So this equation is the equation that you would study and memorize in your physics class for parabolic motion. And what it computes is the height in this object which I was throwing, right, was the marker. So it will show and trace. So if you call this, you know, 1 second and then 2 seconds and then 3 seconds, so the object would be at 1 second, at 2, at 3, at 4. Obviously all the other times in between, but we can clearly find the height if we know the time. Now recall that I tossed the object using a different strength, right? Which means that some of the markers went right down because I didn't use a lot of what we call initial velocity for the object. By the way, if I use initial velocity 0, as you can see, right, it does not propel it forward at all. So the difference between dropping an object and throwing an object is exactly this v0, right, term. And then you also have the y0, which is the height from which you throw. So the height of the marker is going to depend on how strongly you throw, which is v0, and from which height you throw, which is the y0. So over here, we'll call this initial velocity, and we'll call this one initial height. So those are the two terms. Now, we are actually interested only in equation, right? Most of the people just skip physics of it, but there's just so much that you can gain out of this one equation. Now, as I said, eventually we are going to learn how to obtain this equation from a simple statement and differential equations. Now, what is the velocity, right? So velocity is going to be the derivative of position. So if you take the first derivative of the position function, you will get velocity. And we have this square, which will cancel a half. So what we have is negative gt plus v0. The derivative of t is 1, and then the derivative of y0 is 0 because it's constant. So this over here is the velocity. Now, some of you probably took some physics in high school or taking physics now. You probably see an equation which says final velocity is initial velocity plus acceleration times time. That's that equation, guys. It's the same equation, except my acceleration now is gravity minus. So you see the minus g? That's your a, minus g. So this is the same equation. When you have your final velocity, which is what you want to compute, as the function of initial velocity, and then the adjustment term due to gravity. So we have the velocity function obtained by taking the derivative of the position function. And then we have acceleration function. Acceleration function in time is going to be the second derivative of the position function or the first derivative of the velocity function, which is in our case just negative g. And there it is. So that will be acceleration. Now there is another one, another concept called jerk. And that is the derivative of acceleration. You experience jerk every time when you slam too harshly on your gas or a brake pedal in your car. Remember what the purpose of the gas pedal and the brake pedal are, right? The purpose is to either accelerate the vehicle or decelerate the vehicle. Both pedals are actually acceleration. Now, one is one way, the other one is the other way. Because the two pedals are changing the velocity of the car. Now, what is acceleration? We define the acceleration as the change of velocity, right? So the derivative of velocity. So that's what acceleration is. Now, the two pedals are going to be changing velocity of the car, so those pedals are accelerator and decelerator. Now, what happens when you slam too harshly on either of them? You experience jerk, right? So the rapid changes of acceleration produce jerk. So you either, right, hit the face into the steering wheel or hit the back head into the whatever cushion is there on the car. Headrest, thank you very much. Which is why it exists. Otherwise, you will be breaking the neck over the top of the seat. That's designed to protect your life, actually. That's one of the safety features. It's not there for decoration. Or comfortable driving. Of course. Oh, Teslas, come on. Soon you'll be able to take a nap. You just say, car, take me to the closest bar. You sleep on your way back, you sleep on your way back. Right? Anyway. So we have 3 levels, and then there is the 4th level, which we are not covering in this textbook, but I just wanted to point out that it exists. I could add that as well, which is the 3rd derivative. of the position function, second derivative of velocity, and first derivative of acceleration. So the change in, but we do not use it in our calculations, but I just wanted to make sure that you know it exists. And just because you're experiencing it every time you drive, erratically. Now, let's see what we can do with these equations. So, if you have an object that you throw, you can compute objects velocity at impact. You can compute objects maximum height, because at some point when I throw this marker, it reaches the maximum height and then it keeps going down because it's the downward opening parabola. There has to be a maximum point with the horizontal tangency at it that it will have the maximum height. So let's take a look at, I'm going to pick a problem from homework. You can read the ones that are worked out in the textbook. I would see most of you already did. So here is the a stone is thrown vertically on Mars. So this is part of problem 18. So S of t is equal to negative 6t squared plus 64t plus 192. So this is our equation. Now, the Mars gravity is about a third of the Earth one, right? The gravity on Earth on average is 32.2 feet per second squared, and as you can see, gravity is 12 feet per second squared. So clearly it's a smaller planet. So you can jump higher, actually. Anyway, so this is an equation, right? We have it. And now we can obtain velocity equations. Like a velocity equation by simply taking the derivative of the position function in time. So this would be negative 12t plus 64. That's our velocity equation. And we can get the acceleration by simply taking the derivative of velocity, and that's going to be negative 12, as I mentioned earlier. So these are the three equations now that we have, which would govern the motion of something that you throw on Mars. So now, what can we compute? Well, first off, we can compute velocity, acceleration of the object at any point in time. You ask me of the, let's say, status at t equal 3 seconds. All I need to do is to compute S of 3, V of 3, and A of 3. Now, obviously, A of 3 is always negative 12. I don't have to compute that, but I can compute the rest. So what's S of 3? So this is 3 seconds later, right? It's going to be negative 6 times 3 squared plus 64 times 3 plus 192. And we can compute this. So that's 9, that's negative 54. Plus, and then this is this is 192. Plus another 192. So this is negative 54 plus this is 384 for the total of 330. So after 3 seconds, this object is 330 feet up. Velocity of 3 seconds is going to be negative 12 times 3 plus 64. And that's going to be negative 36 plus 64, which is 28. Oh, I should write feet and feet per second. And acceleration at 3 is the same as any other acceleration, is always negative 12. So I can get all of the specs on this. Again, everything depends on this equation over here. You take a physics class, you learn how to come up with this equation, how to measure initial velocity, how to measure properly initial height, so that you can plug those values that you need to actually have the equation. And then some derivatives and you're done. We can also look for max height of the object. And this is a very important problem. We are going to again look at the experiment here. I'm going to toss this marker in the air. Now observe that the marker is going to stop at the highest point and then change the direction and come down. What is the velocity of the marker when it stops at the top? 0. Now, do we have equation for velocity? Yes, we do, right? So if we set that equation equal to 0, you are going to compute t, right? That's the only unknown variable in the velocity equation. So you have the velocity equation on top of the screen, and when you set that one equal to 0, because the object stops at the highest point, you are able to compute the time at which the object reached the highest point. At that point, right, the object is going to go down. So here's the experiment. If you missed that, here's again. Right, so the object stops at the top and then comes back down. So to find the max height, we first find the time at which it occurs, and we use that time in S equation to compute its position, its height. By the way, I'm not sure if I mentioned this, probably not. Acceleration is A of t, A for acceleration, and then velocity V for velocity, and then S for position, because there is S in the word position, right? So it makes sense. Good. So now what do we have? We have the velocity function v that we have as negative 12t plus 64. That's equal to 0. And then we have from there that t is equal to 64 over 12. You can keep canceling this. 64, that's 32 over 6, and that's 16 over 3. So 16 over 3 seconds. So at time, 5.33 seconds is when we have the max height occur. Now I want to actually calculate the exact, so 16 over 3 over here. And that's going to be our negative 6t squared, so negative 6, 16 over 3 squared, plus 64t, so that's 16 over 3, and then plus 192. And when you compute this, you are going to have the max height, because max height occurs about exactly 5 1/3 second later, and then at that point the object will start going down. So this is one of the 3's will cancel with the 6, so I'll have negative 2 times 16 squared over 3 plus 64 times 16 over 3 plus 192, right? Over 1. So times 3 for common denominator. All right, what do I have? I have 2 times 16 times 16 plus 64 is 2 times 32. So 2 times 2 times 16 times 16 plus everything over 3. 192. Now I'm lazy. 16 into 192. How many times? Once. 12, right? Times 16 and then times 3. That's what I have? I hope so. It's just, I don't want to compute with a calculator. I'm lazy. That's what I said. It's right there. Pay attention. Look, it's right there. It says -2. I'm doing the calculation this way for the number just because I'm lazy. I don't want to do the rest. So I can factor out 4 times 16. So what's left? Take 4 out of here. 4, so -8. Plus 4 times 16, there's a 16. Plus, that's a 3, 9 times 16. Over 3. Nine times 16, that's 160 minus 8. So 4 times 16 times... that's 10 16ths, so 160, 152. 1 plus 5 is 6 plus 2. None of this is divided by 3. Wow. Now I have to do 152 times 16 is what? 2 to the 4 and 2 to the 6 over 3. All right, good. There we go. So what do I have? 152. I need to double it 6 times. So I have 304, 608, 1216, 2432. It's 1, 2, 3, 4. 4864. That's 5, and double it one more time, and that's 9, 6, 7, 2, 8. 7, 2, 8 over 3. Is that good? I mean, you can plug this in a calculator right here and just get it. But you can also do the calculation. So feet, there we go. We can actually, well, let's see, the approximate height is 3, 2, 4, 2, and then 0.2, so 2/3, 6, 6, 6. There you go. That's good. Nice. Got it. So about 3,000 feet. Good. So that's the velocity, guys. We throw something and it gets this parabolic motion. And we can describe that parabolic motion in terms of the equation. We keep taking derivatives till we get to acceleration, and we have the formulas. And then when we have the formulas, we can compute the location at which the object is at all times, and we can also calculate the maximum height. And yes. Hello and welcome back to the part 2 of our lecture on derivatives as rate of change. So we discussed the motion, the position function, velocity function, acceleration function, and the fact that these functions are derivatives as we move from position all the way to acceleration. And we did the example where we took problem 18 from the book, where we had an object that was thrown upward on Mars, and we went through calculations to compute what happens after 3 seconds, and then also went along to find the maximum height. Now, there is this notion of measuring things using also the average change. So I need to bring, before we move on to the next topic, which would be the change, let's say, in population or something, let's talk about the average versus instantaneous. So average is a change over the interval, and instantaneous is change at a point. And I really want you guys to associate this with video and photo. If you observe someone, let's say a kid growing up, right? Now, not practical, but let's say there is a video of this kid growing up that takes time, right? You do a time lapse. So this over here would be the video because it's over the interval of time. And this over here would be a picture because it is the snapshot in a split second of time. It's at the point. So you can say this is the, for average, right? This is the interval as I was growing up. So there is a video that it's, I don't know, a year old, and you can see in that video this kid actually growing, right, in size, in height, right, maybe weight as well. So that's what average is, right? It's over the time, and it takes all of that and smooths it out. Where instantaneous, snapshot in time. So let's think about these concepts. You see, while driving, you are driving at certain speed. Speed is the magnitude of velocity. Velocity function is a vector function because it has the direction. You have to be going on 78, 65 miles per hour forward, and that's velocity. Now, we all kind of value our lives, so we all drive the proper way of the highway. So there is no need for velocity limit to be 65 miles per hour because we are all well informed on the direction you should be going on. Now, that takes part from someone, you know, coming on from England, right? But, or the guy that I've seen in Hillsborough 2 weeks ago that, you know, instead of going around the island into their lanes, he went before the island into the opposite lanes. You know, other than those, rest of us pretty much understand that we should be going with the flow of traffic. So there's no need for a velocity limit. We do the speed limit, that is just fine. Now, observe this. Between points A and B, let's say there is a 10-mile stretch. And if there is a 10-mile stretch, it takes you 10 minutes to get there. You can say, so I live 10 miles away from RVCC, and it takes me 10 minutes to get to RVCC. you can calculate the average velocity by simply stating that if you left at 0 miles per hour and if you left at 0 mile marker, no, actually wait, let's do the exits on the highway because they're all mile per exit. So you enter the highway at exit 16, that's Clinton, and you exit 78 at exit 26. So this is mile marker. At the highway, ideally you should have all the exits are miles. So exit 26 is 26 miles away from where the 78 begins in the state. So you have for the distance, right? We know that the velocity is distance over time. So the distance is 26 miles minus the 16 miles, and that's your distance that you're covering. And then let's say you left at 3:27 p.m. and you arrive at 3:37 p.m. So now that is going to be the difference in time as 37 minus 27, which gives you 10 minutes. So now as you are computing this average velocity here, you are getting 10 miles over 10 minutes. Now we don't like minutes because we want miles per hour. You do the same conversion you do in your chemistry courses where you put the unit that you don't want in the denominator to cancel and the unit that you do want in the numerator. And then you say 1 hour has 60 minutes. Great. Now 10 and 10 cancel. So what do you have left? You have left miles per 1/60 hours, and then 60 goes on top, 60 mile per hour. So if you drive 10 miles in 10 minutes, you are actually going on average 60 miles per hour. Now let's say that this is Highway 22. Now I know the speed limit is 55, but apparently everyone drives just a suggested one. So looking at the highway, you have traffic lights, right? You hopefully stop for those. So that's the convention too. Yeah, forget about the ticket. Someone can erase you from the other, right? So don't, right? Make sure you stop if it's red. So you know that you are not going to drive 60 miles per hour flat from Clinton to RVCC. There's no way. Because you are going to hit at least one red light, or you are going to hit at least one car making a U-turn, right? I mean, not hit, but I mean, you have to slow down not to hit the car. Or you'll be stuck behind Knuckles. So there are reasons why you might not be able to go 60 miles per hour from point A to point B. But look, if 60 miles per hour is your average, that means that for all of those velocities, speeds that were below 60, you had to have over 60 to compensate. So like an exam, if you have a 50 and the pass grade is 70, you have a 50, the pass grade is 70, well, next exam better be 90 so that these two can average to 70 each, and then you have 70 everything, right? This one doesn't count because that one is a pass. So whatever the differential is between these when you are below has to be the differential on the next exam to make up for the loss on the previous one. So this means that if you had to drop your speed from 50 sorry, from 60 to 40 because someone just cut you off to get in, that means that at one point you had to be driving 80 to make up the, right, if the average is this. Now, you're not going to find people having average on 60. I mean, maybe you will, but hopefully not too many, right? So the 60 mile per hour average on 78 is what everyone has, right, and more. But on 22, no. So that is your average velocity. As you can see, it takes the entire trip and it smooths everything down. The trip that could look this way for velocity. Clearly you start at velocity equals 0 because I don't think that you are jumping into the moving vehicle. So there is no V0 there, right? The vehicle is parked when you get in. And then you accelerate, so velocity goes up, and then you drive, and then there is a stop sign, and then you accelerate again and drive, and there's a red signal, and then you drive, right? And then when you come here, you also have to slow down and navigate the parking lots and then stop, right? You don't jump out of a car at 60 miles per hour, right? So, as I said, the average is going to be taking all of these times that you had below and averaging with everything that was above to give you the average value. Now, what is the instantaneous value? Instantaneous value is the one that you get the ticket for. Instantaneous value is the one that if you get clocked, it shows up on a police radar. That's the one that you get clocked for, instantaneous, and that is the derivative. So, your speedometer in a car adjusts immediately when you touch either the gas or the brake pedal. And that one shows instantaneous velocity. Velocity at every split second, right? At every instant of time. And it changes rapidly as you keep pressing different pedals, right? So there is no so that's the instantaneous velocity. So instantaneous velocity is the speed that you have at the moment you observe, right? So that's technically what it is. So instantaneous velocity would be the derivative, which is the speed at the moment or at the instant of measurement. And the measurement is when you look at it, right? You see the lights in the rear view mirror? The first thing you do is you look at the speed, right? And you go, 5 points again. I see some of you can relate over there. You have 200 points?
What?
Did you say you have 200 points?
No.
No? I'm sorry?
Yeah.
Yeah, I don't know. I don't have any, so. I don't even know. Does anyone?
After 12, they take your license away, I thought. And then to get points reduced, you have to go to a class and then we'll remove it.
So 12 is the limit?
Yeah.
It's not? You can have more than 12?
Crazy expensive. You can have more than 12 points.
Oh, and so insurance is the expensive one. So you apparently can have more than 12 points, apparently. Oh, the license goes away? Okay. All right. Sounds good. Growth models. Let's see. So hopefully you remember those exponential problems from your pre-Calculus 1 class, where we talk about growth of population or decay of mass, the radioactive decay or decay of garbage or, whatever. So now we're talking about these because we can also talk about the rates at which the population grows. There is a lot of heated debate, which I don't know if you follow or not, on the carrying capacity of the planet. We are actually having a crisis on the planet due to overpopulation. Now you'll say, yeah, 7.4 billion people, but then we are also looking at the carrying capacity of the planet that is moving, depending on which research you look at, anywhere from 10 to 15. And a lot of people think like 12 is already too high. Now, the issue with that obviously is the finite surface area of the planet for housing and everything else, ever expanding deserts, because the wind spreads the sand out, so all of the deserts are expanding, which is obviously taking the soil to grow food. And then you also have the rising seas due to the melt of the polar cap and so on. So now, the surface area on which we can live and build is decreasing, and the deserts are obviously expanding as well. As I said, also the resources in terms of energy. Fusion is always 30 years away, right? So and it's been like that since the last 30 years. So we have issues with not having a place for nuclear waste because we don't have fusion and we can't produce enough energy to charge all the cell phones and everything else. We have issue with clearing the rainforests to get more soil to grow more food. We have issues with burning the coal primarily to have the electricity where it is. So you pick your demon, whether you want the global warming to go up because of all the coal that produces the electricity, and the cars contribute obviously, or you want the nuclear fission, which is bad because of the nuclear waste. Now fusion, you put in deuterium on one end and you get water on the other end. So technically infinite energy for free, but it's a big feat to get that working. So we have all of these crises that a lot of people don't even pay attention to, and we should, as a species, worry about it, because no matter what we do and when we all die, the planet is still going to be around, going around the sun. No one cares, right? We are actually just making situation worse for ourselves. The planet is going to be fine. That's why I don't like the people who say save the planet. You just grow up. You don't get to save the planet, all right? You're nothing. You're no one, right? That's the way the planet sees you, and that's the truth. The only thing that we need to preserve is the environment. We need to preserve environment because it harms us. We can't live in garbage. We can't live in filth. We can't live in weather that is unpredictable because of the global warming and all of these kind of things. So now, all of these issues are all connected, and they're all connected through exponential functions. which are great to consider to look at the models for population. Now, to simplify all of these things, I'm going to talk about population of rabbits, because that's simple. Now, what you can do is you can go to Google and ask for the population of humans, let's say 100 years ago, and then ask for current population, and then find your own model for population of humans, and do exactly the same thing that I'm going to do for rabbits now. So what do we have? Let's put a habitat for rabbits, and so we are going to put up a habitat. There's going to be food for rabbits, and we're not going to use any of the advanced models. So let's not put any predators and things like that. So I'll just have the rabbits run around. So let's start with population. And I'm going to say 500 rabbits. No school tomorrow. All right, let's go home. Oh, really? Look at that. By the way, I'm just going to make sure that you understand that you paid for the class tomorrow that you're not going to be at. And, yeah, no one's going to reimburse you for that one. So don't be happy. Be angry.
So sad.
Actually, what I always wanted to do, and this is a missed opportunity, when all the phones ring, everyone answers and puts the speaker up. Because I just wanted to hear John from 20 locations say the same thing. He's an awesome guy, I love him, but yeah. Anyway, going back to this, so 500 rabbits. We have 500 rabbits that we are going to put into this habitat. And that's the beginning of the universe for these rabbits. Now, we are going to wait, let's say, a year, and then we're going to count all the rabbits. There will be new rabbits jumping around as well. And let's say we count, after a year, 600 rabbits. So, a year later, I really don't know what the dynamic of rabbit multiplication is, but we're just for the sake of the problem. Because I want to see what I can calculate once I have the functions and everything else. So these are the things that you can measure. Now, guys, I don't care if you talk about rabbits, or you're talking about wolves, or you're talking about bacteria culture in a dish, or humans on the planet. Mathematics of the thing is going to be the same. It's just, let's have some controlled environment that we can understand and we can calculate quickly. So we have 500 rabbits. So we are starting with 500 rabbits at time 0. So time equals 0. Initial population is 500 rabbits. The equation that you know from your pre-Calculus 1 class is that population of rabbits in time is initial population times e to the kt. P0 is going to be your 500 initial rabbits, and then all of the characteristics of rabbit multiplication and death and food and whatever other things go into this are going to be within this K. And that's very simple to, as you can see, calculate. So where do I start? I have now, after a year, the population of rabbits is 600. So I have 2 points in time. I will use the first point, right, to write the model that population in time is now 500e to the kt. and then I'm going to use the second point, 1 and 600, to get k. So that's going to be 600 is equal to 500 times e to the k, because t is 1. Put times 1, whatever. So now this is going to be 6/5 equal to, leave some space, e to the k. What I have over here is exponential equation that I need to solve for k, and I achieve that by doing what? How do I solve this? Log. Good. So we are going to ln both sides. And we have that k, right, ln and e cancel. We are going to have that ln. Oh, I got a call from John too. Look at that. Counter-Strike, anyone tomorrow? PUBG? Okay, sure. We can. So we are going to go with the ln of 6/5, which is 0.1823. We are using 4 decimal because these exponential functions really pile up the error as we go along. So we have a k now, and guys, because we have p0, we have k, we have the model for these rabbits. So the model is population of rabbits in time is 500 e to the 0.1823 t. So this is the math model for this situation with rabbits. Now clearly, if you counted a different value other than 600 after a year, that will change. So we have our equation. Now I can use this equation to calculate years. Again,